Okay, so if nothing else, then we're going to jump into storage, which is my favorite presentation. I'm very hyped about storage. I hope you all will be too. And it's super important. And it's a little bit long. But yeah, so again, we're going to do storage. We're going to make our way through the whole slide, hopefully. Some questions in between. We'll take a small break, live coding till the end of the day, and then go from there, okay? Cool. Any questions about, or any comments or questions about frame storage before we get into it? Obviously, you already had a presentation about Merkleized storage and substrate storage, right? I hope everyone feels pretty good about that content. I think I will just very briefly review the most key points, but I think what's really important is, and don't be honest here, that if there's something related to these first couple slides, that's the storage layers, overlay, the Patricia tree, the Merkle tree, stuff like that. If anything like that doesn't make sense to you, let's solve that problem now before we get deeper into things. You're just gonna get lost, okay? So feel free to raise your hand or nudge a neighbor to raise the hand to get that information out there, okay? Great. Frame storage. So in this presentation, we're gonna go deeper into the concepts of substrate storage, see what kind of storage primitives Frame exposes to you and how it all connects and makes palette development easy, okay? So as you've already learned, in Substrate, there are different layers to the storage system, right? You have the runtime storage API, storage overlay, Patricia Merkle tree, key value database, right? And these two pink boxes are more about where you as a developer touch. Like you're not really as a developer touching the core Patricia Merkle tree or the core low-level database, right? We've made a lot of optimizations here already. I don't know if it's been mentioned that we use this thing called like the Parity DB, right? Instead of like RocksDB. We have made a lot of optimizations here, but really these are the areas in which you touch these APIs, and that's what we'll focus on mostly here in this conversation. These layers make sense, right? Okay. So, and you guys, did you guys already cover overlay? Okay, let's go over it one more time just to make sure. But yeah, just a quick overlay deep dive. So I assume you haven't seen this picture before, right? Okay, so but you've probably seen things like it. But basically, the overlay is a way that we can stage changes to the actual database. So writing to the actual Patricia Merkle tree is super expensive, right? Like not only is it actually like writing to a database, it's passing through these layers, but also having to calculate the Merkle root, all that kind of stuff. What we have in this overlay change set is this kind of very light DB in memory, which I think isn't even Merkleized. It's just raw key value things. So if we can do all the operations there and then queue the changes down, it's way more efficient, way better for us, right? So let's go through that. So let's take an idea of a balance transfer. Let's walk through the steps. Well, first, the runtime logic at the very top initiates, okay, we want to do a balance transfer between some users, right? This will call the runtime storage APIs, right? It will come to here. Do I have arrows? Let me see, do I have arrows? No. It will come to the runtime storage API, right? The runtime storage API will look first at the overlay change set. Do you have the information I need to proceed? In this case, the answer is no, right? So overlay change set then passes down through the database interface to the actual database and will actually fetch the information it needs to complete the transfer. So I think in this case, we're doing a transfer from Alice to Bob. Probably the next one, we'll see that. A transfer from Alice to Bob. So the process of runtime logic asking the overlay, do you have the information? It says no. It's doing a very expensive read down to the database to pull that information up and put it in the overlay. But now, subsequent reads to this information and subsequent writes to this information is very cheap because it's right here in the overlay already, right? So as we return the data back to the runtime, we cache the values. Subsequent reads and writes are very, very, very cheap, right? It's very nice. Okay, and then the runtime logic will actually execute and update the balances. We'll take 5 from Bob and give 5 to Alice, right? And you can see here we have modified values in the overlay change set, but the database still has the old values. But again, every single time you're reading from the runtime, you're hitting this first. So you're never going to get the old values. You're always going to get the new values, right? So this keeps you that you're always up to date, right? And then finally, when at the end of the block, when all of the things have been done, we actually push the changes down to the actual database. We only try to do this once because it's very expensive and we can do it all at once. And then actually the database will be updated.
Question. So when you said like initially it goes to the overlay and it says like, okay, there's nothing here, go to the database, right?
Yep. That's
nothing here, meaning, so basically it's just looking for the existence
of a key.
Value.
Exactly. And you know what? This is one of those things, right? If the key doesn't exist in the database either, the overlay needs to go down and check. I believe there's probably a state in the overlay that says that this key doesn't exist. But of course, you don't know it doesn't exist until you actually go try and query it, right?
Yeah, sure.
Yeah. But that's basically it. Like, here, the overlay has no knowledge of the key that you want. So it has to go to the database to ask for it. Yeah, one more in the back. Can we bring the microphone to the back, please?
What about concurrency if two calls are made and update values in different?
Thankfully, the runtime is all synchronous. We're working in a synchronous environment, the runtime, right?
So the RPCs, they are queued?
The RPC queries, so that's all reading, right?
No, I mean, even for writing. If someone calls the...
So
I suppose that these logics come from an external call that someone is sending a transaction to the node, right?
Yes, but the only way that this, at least in the context of runtime database, the blockchain database, whatever, the thing that we care about, the only way that these values are updated is through the runtime. The runtime is the state transition function. This is the state, changing it is the transition. The only access to these changes is through the runtime, and the runtime is a synchronous environment.
Okay, I got it. So the calls come in parallel, but the runtime has ways to deal with these parallel calls and enqueue the...
Yeah. So what you're missing is the transaction pool. So there's the transaction pool orders the transactions, and then we create a block. A block is defined as a full set of transactions in an order, and then we execute the block.
And every block is executed at once. That there's no two blocks being executed at the same time.
So there can be, from the perspective of the client, there can be. The client could be doing things in parallel, but in the context of the runtime, you are in one block. Like you only see one block. You think that you're the true state. Yeah. So in that case, there's only one true. Well, I'll show you more. There's ways to do things where there's multiple databases, but the trick here, I'll show you. The client can do clever things that can support parallelization of things, but in the context of one runtime state, there's only one value. But there are tricks that you could support multiple versions of the value. It's actually very cool. The Merkle trees, man. Merkle trees, awesome.
So, Mirsha, so one thing is in the overlay chains that commits to the DB and everything. Once the block is finalized in terms of block execution, like finalization or like consensus.
Just end of the block. End of the block. So it doesn't have to be finalized for consensus. It just needs to be the end of the block.
Oh, so block finalization is in the block process.
Yeah, that's that. Yeah. Do I use the word final? I guess storage root committed to the database at once at the end of the block. Yeah. So it is not about finalization. Finalization is a consensus thing. That's not needed. This is more of a mechanical thing. At the end of the block, once the whole block is valid, then all of the state transition functions, all the state changes are committed.
So for example, in the executive, there is block finalized block, like that API for finalized block. So
but that's not final. That's not consensus finality.
Yes,
that's just poor wording.
Building finalization. Right?
Yeah. This poor wording. Truthfully, we should fix that. So one of you should yell at Keon, not me. Okay. Overlays in memory. It's an in-memory database. Very fast. Yeah, so the implications. So what are the implications of the overlay change set? It's this. Reading the storage the first time is slow, but reading the same storage a second time or more is fast, very fast. Not free, right? It still needs to read some memory, but it's very fast, okay? Same, writing to the same value multiple times is very fast, very cheap. But obviously, one time it'll write to the database, it'll be very slow, right? So there's kind of one expensive read, one expensive write for every main operation, and all the other ones are kind of subsidized by the overlay change set. Very cheap, not the cheapest, okay? Well, not free, yeah.
And that's per block?
Per block.
Or per extrinsic?
No, it has to be per block because, again, in the context of how the blockchain works, there's never just one transaction by itself. There's always a block and a set of transactions. And either that whole block is valid or the whole block is invalid. Even if there's every transaction is good except for one, that whole block would be invalid. So we only commit once a block is valid. Okay. So let's extend the idea. Why don't we add additional layers? We can do that, right? So there's additional things called additional storage overlays or transactional storage layers. So we have the ability to spawn additional storage layers called transactional layers, right? This allows you to basically do the exact same thing as the overlay change set, but you have control over the layers, and you can control basically when you want to commit things down the stack, right? You can spawn multiple transactional layers at different times, and you can basically control the functionality. So in this case, we have added additional transactional layer where we can, in our runtime logic, control that we're making some changes up here. And then we can choose in our own runtime logic if we want to drop this layer and not actually commit it to the overlay, or actually commit it. What do I have here? Is there another slide? Yeah. So I don't have another slide here, but basically you can make some changes in a layer that you can control, and then you can choose to drop it or to keep it. Once it makes its way into the overlay change set, it will get committed to the database. There's nothing here to undo from the overlay change set. The overlay change set has the latest state. But if you wanted to create your own layer, do a bunch of operations, and then discard it, that's fine. The overlay change set will not be affected, okay? So let's give an example of why this could be useful. This could be useful for smart contracts, right? Smart contracts, you can execute some smart contract transaction, do some updates, but then realize the transaction would fail or run out of gas, and discard that, but still charge them the fee, right? The fee could be happening at this layer. The contract logic could be happening here, right? Other things you could do. Let's imagine you have some really complex logic where you have some tree, it goes down some other tree, you're constantly changing storage, but then you realize at the very end of the process, this isn't a valid state. Maybe like a flash loan, right? You do all of these exchanges and changes, and at the very end, the user doesn't have enough to pay back the flash loan. You drop the state, unroll all the changes, it never makes its way to the database, right? You can still charge fees or whatever, but you can spawn these layers, and you can control as a runtime developer when you want to actually commit data to the blockchain. And again, when you spawn a transactional layer, when you read the data, you're always reading the most up-to-date state that you know, right? So it's not like you're getting confused between layers. Does this make sense? Yeah, one more question? Yeah.
Just clarification in terms of, so it's kind of like allowing stateless transaction in terms of like, we don't like commit anything to the DB. We just have like a temporary DB to work on this stuff, and
then we
maybe
can choose
for that. Yeah.
Yeah, I don't necessarily like your wording to stateless transaction. I'm not sure what that means. But what I'm really saying here is that you have the ability to queue changes to the database and either push them all or drop them all. And you can do that multiple times. So you get to define a layer which you can queue DB changes, and then you choose at the end if you want to push it or you want to drop it. And that's powerful. And this is all possible due to Alex. I think Alex didn't present this time in the PBA, but he's a really awesome dev, and he was able to construct a really lightweight model for supporting this kind of transactional layers. Like this kind of stuff usually is very expensive. He made it fast, with Rust magic. These guys are wizards. Here, I talk about it still. So the transactional layer implementation details. It is a non-zero overhead, but very, very small. So there's about 0.15% overhead per key written per storage layer. So if a writing to the database costs, like 1 second of time, here it's going to cost 1 second, 0.0015, right? Super, super little per key written per storage layer. One of the ways that it's so fast is that values are not copied between layers. Instead, the values are stored on the heap, and we move pointers around. So it's all using pointer magic to make this all work. And so the overhead has nothing to do with storage size. So also when we're dealing with large storage items, this layer stuff has no, the size of the storage is not really affected. It's just pointers. These are all fixed length.
Question.
Yeah.
In terms of like size, like in some cases the pointers can be like bigger than the actual data. Like if you're
Yeah, but I mean, on average, like, you know, but again, another thing is with a CPU architecture, as I understand, pointers are like, they fit exactly into one chunk, right? So it's like, you don't really get benefits from, yeah, it's a U size, right? So you don't really get benefits for being smaller, right? Everything has to be at least U size in the CPU.
Well, I think like if it's like a zero type, like just an enum, for example.
To be honest, you talked to the wrong guy. I'm a PM for Microsoft. I don't know. I don't know this level of stuff, but yeah.
You're saying that the values are not copied between layers, but is this true also for the transactional layer? Because
that's what, for the transactional layer. This is the rules. These are the rules for transaction. This is the implementation details for the transactional layers.
But then if they're not copied, if they're pointers and you're changing the pointer like directly, then how are you going to like just discard the layer and keep the overlay layer as is? Okay, to understand, you're saying that the transactional layer has pointers to the overlay.
To the heap, no, to a heap. So I'm saying that somewhere the balance of Alice, you know, like, so let's go back to this slide. Somewhere in the memory, there's that Alice has 15 and Alice has 25, right? This is all stored in the heap. But we're not actually moving around 25 places. We just have pointers to like 15 state, 25 state, and this is all pointers, right? And at some point, we actually take the data and then we push it down to the database and then resolve from pointers to data, right? There's one more. Okay, no. So let's do this. Finish this. So the overhead doesn't do the storage size, and then storage layers use client memory, so practically no upper limits. So it's all on the client side. It's very, very, very powerful. And then in Substrate, we have storage layers by default, right? So in Substrate, there's always going to be a storage layer above the overlay. We always spawn one when you do an extrinsic. So whenever you submit an extrinsic, or you write any new call, we spawn one storage layer for you. And then if that call fails, we unwind any changes. So that means when you're writing an extrinsic, you can actually write to storage, do all these things. And if there's an error at the end, none of those changes will be propagated, right? And of course, you know, if you want things to propagate, you could spawn your own transaction layer and push things through kind of manually, you know? So it's still possible to do things. But the idea is that you get the same behavior as you expect from smart contracts in the runtime system at a very low cost to you as a developer, 0.15%. Okay, but there is an attack vector. So we do actually, well, I'll tell you the solution later, but there is a way to attack the system using transactional layers. What you want to do is you want to spawn a bunch of layers with no changes in them, and then at the top layer, make a billion changes, like as many changes as you can fit up there, and then propagate those changes down. Because every single time, you have to say you have a billion changes, you have to bring a billion changes down to the next layer, then a billion changes down to the next layer, etc., etc. So let's imagine that you somehow measure, or you like, you know, the cost for a change is not being measured correctly. You spawning all these empty layers is low cost to you, but then you spawning a bunch of changes up here actually has much more impact than you doing a kind of an even amount of changes across all the layers, right? You're pushing things down. So the way that we solve this is basically we do not allow users to create an unbounded number of layers. In Substrate, I believe there's a limit of 256 layers. Maybe 255, I don't know, whatever the count from 0. But basically the idea is that you can only spawn so many layers, and when we do benchmarking or when we measure the complexity of our system, we assume always that all your changes are at the top layer. So we always assume the worst case scenario. But in this context, again, it's, you know, the overhead is basically insignificant. It's within the error of a computer running the program, like the machine being warm or cold. Explain one more time. Yeah. So the attack. What's the attack vector? The attack vector is this. When you're spawning layers, the expensive part of the operation is when this layer is being committed down to the next layer, it has to do some work, push down. So the attack vector is to make a lot of layers, make a lot of changes up here, and then tell them all to commit. What happens is that every layer, we're committing a bunch of stuff every single time because we don't know, like we basically have to commit all the data every single time to every single layer. Yeah, microphone? And what I mean by data, I mean pointers. Yeah, it's just we're chunking it down, exactly.
And so the dev is the one who's creating
the layers.
the layers. So
Yes, this is the runtime. Runtime, you control this.
yeah. So what's the?
Well, I mean, you
it's
could also.
basically like you're saying that if like an attacker can identify the fact that there are many layers, and then you.
Well, what I'm saying is this: that you, as a runtime developer, control the logic to spawn a layer. You
Yeah.
could make an extrinsic called spawn layer, and if you don't, if you're bad about your coding, and you let's say you put spawn layer inside of a for loop, and you let the user control that for loop, then you're exposing yourself. Now we have a limit inside of Substrate, so when you try to spawn the 256th layer, it will error. So that helps you. What I'm trying to, and we solve this problem for you. What I'm saying is that you can actually even bypass these limits with some Rust code. We have like a spawn transactional layer safe and spawn transactional layer unsafe. We have these things. So what I want to tell you is, you're God. You have control over these kind of things. You should be aware of the attack vectors.
Okay.
Yeah, follow-up question on it. So my question is on there. You said the attack vectors when there are many layers, and if you want to commit the top level layer to the DB, you have to kind of like go down, commit.
Exactly, because you don't know where the other changes
are.
are.
Committing, are you copying the data or changing the pointer?
The pointers.
So okay. So if the pointer is pointing on the latest data, right? So and the data on the top one is kind of the latest one, right? And the like below layers are kind of like having the old data, right? So you have to like copy it, right, to down. Like
I know what you're saying.
Yeah.
So in this case, this is the latest data. Why don't I just skip all the way down to the bottom? It could be that this wasn't populated, but there's a change here.
Okay.
Right?
Okay.
So we need to like find all the changes.
Okay.
So this layer may not have this change, but this layer may have this change. We need to find it.
Okay, but also, are we like copying the data by going down or like
The pointers.
The pointers only.
The pointers.
Okay, so like you're changing the pointer and then just take the resulting one to
Yeah. So at the final layer, we have the list of pointers which point to the latest data, and then we commit. Then we take the pointers, grab the data, put it into the database.
And is there also a possible case where basically we'd have like the overlay here,
Okay.
and then a transaction layer here, and another one here, like not.
No.
above
You can't have two different transactional layers in parallel.
it. Okay.
That's because that would imagine runtime. There's only one canonical. It's deterministic, right? There's only one
Yeah.
situation. So yeah, layers they only stack. Okay. Anyway, the main takeaway from all of this is that really awesome engineering work made this very efficient, and that whenever you create an extrinsic, if you return an error, we undo the changes, right? And I think this is the expected behavior, right? But if for whatever reason you want to bypass this behavior, you can. You have the ability to, but this is the default behavior. Okay, now we're going to go to the runtime storage APIs. Any other questions about transactional layers? Great. Okay, so we learned about Patricia trees, right? This is a very efficient structure to be able to store data with lots of redundancy in it, right? So instead of having to store all of these words, we can just store this tree structure where the duplicate data is only stored once, and we're able to recover all the data. This is like a very nice compressed state, right? We're able to combine. Why? There should be a thing that says Merkle tree, and then you combine it and you get this. But basically, okay, so there's Patricia tree, there's Patricia keys, and we look at an actual substrate database, what the actual Merkle Patricia tree looks like. It looks something like this. This is actually like kind of a visualization of that actual true Patricia Merkle tree. So you can see here is that there's two kinds of keys. There is the key path, right, which we turn into a Patricia tree here, right? So like again, you can see that all these keys, they share some different information. They all have A7. Some of them have 7 in this third digit. Some have D, some have 3, etc. We're able to compress this information, these set of keys, down a Patricia tree over here, right? That's the first kind of key. The second kind of key is that these lines are actually keys to the database. Your raw database will have a set of keys where the data actually is. Your data does not exist at a key in the database here. This is just a virtualization of how to navigate the data structure. This is telling you the paths to follow. But somewhere, actually, the data exists in your database. And very interestingly, the data exists in the database equal of the hash of the data. Let's just sit on that real quick. This data, so going from here to here, this line represents a database query. There's a key in a database. In that database, there's a key, there's a value. This is the value, this node, with all this, structure and numbers and all kind of stuff, right? That's in the database. You can find that the database key, which got you this information, is the hash of this value. What does that mean? That means if there's ever duplicate data in your Merkle tree, you only have one copy of it. Right? There's no reason to make. You have a value, it has a hash, that's the key. 1 million people can reference that data. You only need it one time. Right? Okay.
So yeah, one follow-up question is on the Patricia tree. So you said, okay, one thing is we have the key path, right? The first step of the first step of keys, and also like in the node. Okay, so first of all, aren't we storing some value? For example, in the branch node, in the leaf node, we're not storing any value there.
We're storing values in the only where the value nodes are.
Yeah, but then so in the nodes also we can store values, right? In the nodes.
Yeah. So there are nodes without values.
Yes.
And there are nodes with values.
With value. Okay, so one thing Ankan said, like if the value is too big, you just store the hash of it and then reference it to the DB, right? He talk about that.
No, we have to store that. Somewhere we have to store the data. Like
yes.
that, we have to store it.
So one thing is if the data is on the tree, but also like the node in which the path key ends, we hash the node, encode and hash it, and that hash is used as a key to the actual value in the DB, right? So if the value is actually in the node and we're actually storing now it again in the DB, aren't we like double storing? Why can't we just store it in the DB?
I think you're mistaken. So here's an example of like a key end, right?
Yeah.
This is the value. This is in the database. Like you're not storing it again after this. This is the your balance is here.
But isn't that the node in the tree?
Yes, but it is a node in the tree, but it can have a value. That's the leaf node.
Yes.
It has the value. It has your balance. It has whatever information like the block number or whatever.
Exactly. But okay, my thing is in terms of visualization. So there's a tree and then the DB like below, right? The DB just has the key and value.
Pause there. That's already a misinterpretation. There is only a database. The tree does not exist above the database. The tree is an abstraction of the database.
Okay.
Imagine the database is this long table of keys and values.
Yes.
The tree is a hopscotch table telling you how to jump around the different points of the database, right?
Okay.
So it does not physically exist.
Yes.
It is a set of rules to follow on how to navigate. So again, this is an item in the database. I want to go to the 7. 7 will have it in there, a hash.
Okay.
I will query the database at that hash, and I will find this value.
Yes.
And then I will go and find, I want to go 3, there's another hash here, I will query that in the database, go here. There isn't actually a tree, it's just I'm actually navigating the database.
Okay.
It's a rule set for navigating the database. I really think of it like a hopscotch table. It tells you how to get from point A to point B.
Okay, now it's clear.
So the tree is a virtual existence.
So the root here is the red one?
The root here is the red one, sure, yeah. Or it's the very first, I mean.
And what's the branch like terminology here?
Branch. So in this context, a branch here is that it's not like it can have a value. Like here it has a value, but basically a branch means that it's connecting. There's more nodes underneath it. This is a leaf because there's no more after this. But here it's still there's still more after this to find.
And what's the reason it has a value?
Because it has a value because it can have a value. Our database supports that you can have a value at a branch node.
But isn't that value like related to the children?
No. So like this, if I want to query what is the data at A77D3, I get this value. If I want to query what is the data at A7737, I must pass through this to get to the value, right? So this value wasn't what I'm looking for, but this node contains a pathway for me, right?
And those keys, like A7, they are like
these.
Is it like the pointers or?
No, these are this is the key that you will use in Frame.
Okay.
So there was a key code. Oh, I guess you all did this in your exercise, right? You put a key code. This is like CODE. Yeah. Like I guess it wouldn't actually be like the Unicode equivalent, but that is the code you're familiar with. The code you're not the key you're not exposed to. You're not exposed to the database key. The database key, that's all behind the scenes. You're being exposed to these keys, and that's how you access the structure.
How prefixes play the role in all this?
Radix. So yeah, radix is
prefix.
Radix.
The prefix is 0,
prefix. Oh yeah, prefix. Yeah. Prefix is telling you what kind of node it is. So this is 1 is telling you that this is a branch with value. I think this there. Kian should have covered this, but I'm surprised he didn't do it. But like 0, 1 is telling you that this is a leaf node, so that it basically it's telling you how to deserialize the data you're seeing. So there's 4 options. There's branch with value, leaf, and there might be like a null. I don't remember, but something like that. So that answers your question, though, right? Yeah, exactly. So this is just the prefix is just telling you, like, again, this is the way, like, a computer is just reading bytes. So this is telling you what data to expect. It's much like scale codec, right? Like the beginning prefix kind of tells you this is the information you should expect to get, and this is how you decode it. Okay.
Question here. So does this also happen? So a storage key is like the account IDs. We use them as keys for balances, right?
I'll go over that. Yeah, but yes, that's correct.
Yeah, I don't see that this is efficient for something like account key, like account IDs. Why don't, like, it's a hash and then it's a key value and that's it, right?
I'll answer your question. If after this presentation you don't think it's efficient, then we can have a conversation. Like that's a good point. But I think I'll explain to you how we generate keys and all that kind of stuff. But the key thing to take away from here, God, it's awful. The key thing to take away from here is that there's 2 kinds of keys, and this is the one you're exposed to, but behind the scenes, this doesn't exist. It's not real. There's only database keys, right? Okay. Okay. So now finally we're all on the same page, right? We're all on the same page. We've kind of gotten to this point of agreement and understanding. So now finally we're actually going to talk. What does Frame do? How does Frame generate these keys? We follow a simple pattern. We use a series of concatenated hashes to generate unique keys. For example, if you hash the name of your palette, concatenate it to the hash of your storage name, you will find that that will be the tree key, the trie key, to some data. All right, and this is unique, right? For every palette, we'll have a unique hash. The storage name will have a unique thing, and it will go on. Okay? So we'll go into more specific details about this. But that's the idea. The idea is always we're concatenating hashes. Okay. So obviously I already introduced the fact that we can use this thing like palette name and storage name. Let's take a look at that. So the palette name comes from the construct runtime. So this right here is defining the name of the palette. So actually if you change this name on a live blockchain, you'll break some of storage. Right? So like I can import a palette frame system or a crate frame system, and I'm naming it system. And the construct runtime and all of the macros is pulling, hey, this is the name of this thing. And all of these names must be unique. Even Rust already requires that, right? So changing the name of the palette here is a breaking change. Okay, Frame storage primitives. So we're going to go over all of these things. But basically, there's storage values, single value, storage maps, counted storage maps, double maps, storage end maps, etc. Right? So these are all tools at your disposal. You'll see how they work. So let's talk about storage value. Okay? So storage value is placing a single item into storage. And if you look at the definition inside of a frame, it's kind of long. It's kind of something bigger than you expect. There's a struct, storage value, and it has a bunch of generic types here. Some with default configurations. The storage key for every storage value is equal to just the hash of the palette prefix plus the hash of the storage prefix. This is palette name, storage name. Okay? Here's an example. So this is like working code you could put inside of a palette. So if you're in a palette, you want to define a palette storage, you use this, the attribute macro over a struct, or a type, I guess, in this case. And then you can say storage value of U32. And then, of course, if you want to write a test, I think, by the way, I have all of this. I think there's, in the public repo, there's a folder inside of the frame lecture called like the storage example. Let me see if I can find it real quick. So if I go to PBA content, PBA, because you can follow along here if you need to. In PBA content repo, you all have access to this, right? There's a syllabus, there's frame, and then here frame storage activity. I believe this has all of every single. Oh, sorry, you can't even read it. Every single example I have in these slides is exactly here. So it's item 1, item 2, item 3 is exactly one for one here. And then all of the tests I write are here for testing all the things. So exactly what's in my slide, you can run this yourself locally and try it, okay? So if you want to see it. Okay, let's go back to this. No. So you can see here the storage value. Again, that's in the thing. And if you want to access the item, assert initially, when you get the item, there's nothing in it, right? A storage is empty. You can put an item into storage, and then when you get it, it's some value. You have a question? Or did you have a question as well? Okay, sorry.
Yeah, just one question. In terms of the storage prefix there, the dash. So yeah, is it related to the node prefix or it's not? It's not related.
Node prefix.
Yes.
Oh, like the other thing? No.
So that's just.
I will show more detail on prefix soon.
Okay. Sure.
Okay. And your question?
So my question is like, why we concatenating hashes of prefix and.
I will also answer that in my presentation.
Together, right?
Yeah, put it together. I'll explain all of this coming up soon. It's actually a very beautiful design. Okay, but we kind of agree. So we understand the use of a storage value. You want to store one piece of information, you do it. Yeah, question in the back. Can we get the microphone in the back, please?
Wow. Where is the key in this case? The key is the name of the type?
I'll explain that too. I think we should go a little bit further. I'll tell you a good stopping point for questions, okay?
Okay.
Okay, I promise. Because I'm talking about this all right now. So first, do we all understand this? I define some item 1. It uses the macro magic stuff, but it's mostly Rust. And I'm now able to access these APIs like get, put, and get, right, on it. And it does exactly what you expect. It gets the value for you. So now let's break it down a little more. What's actually going on behind the scenes? So what is this storage prefix? What is this thing? You see this? This empty. That's weird, right? If you go back to here, that is the prefix here. So somehow we're passing in like this, autocomplete to Rust. So this prefix is what's used to generate the storage key. This is the information needed and the logic behind the scenes which actually generates a storage key. So this prefix type implements storage instance. And storage instance basically has these two pieces. A storage prefix, which is a string, and a palette prefix, which is also a string. That's the high-level idea. The storage prefix is the name of the storage. So in this case, item 1, that's the storage prefix. And then the palette prefix is the name of the palette, which in this case, is example. Okay? So we have two strings now, pulled from the macros. Okay? And it's all this is populated thanks to the macro magic. So what are we doing? So if we look at the key, so we can actually, one of the APIs on the storage item is to tell me the key. So I can call hashed key, and it will print this line. And if we actually break that down, this is 2 pieces. And if we look, actually, you can find an example. The hash of the word example is this. The hash of the word item 1 is this, and it's exactly the same. So the key for this item, this is again the tree key for this item, is just the concatenation of these 2 hashes. Okay. Let's demystify frame storage. So this is not actually working. This is not actually accurate, but this is a very simple example of exactly kind of what's happening. So this basically shows what's going on behind the scenes here. So somehow the macro magic is automatically populating the struct prefix, right? So it's creating the struct prefix for you, and it's populating it with the information. It's populating it with a storage prefix called myStorage, and a palette prefix called myPalette, and it has a function called prefix, which returns a vec, which is basically doing the concatenation. It's doing the hash concatenation. So basically, given this prefix, given these strings, I can call prefix on it, and it returns to me a key. So whenever then I have my storage, and my storage uses this prefix struct as the associated type, when I call get, what it's actually doing is it's calling SPIO storage get, you're familiar with this API, low level, onto prefix colon prefix. It's calling this function, and it's basically querying in the database this key, right? That's exactly what's happening. That all of this logic is being hidden from you thanks to the macro magic. But it's basically, if you can imagine, we can populate these 2 strings. If you can imagine, we can write this function. All of our functions, like get, it calls this hash. Set, it sets that whatever value you want at that hash. Clear, it clears that at that hash.
Can you just clarify which part is the macro expansion and which part is the actual code that we
The only code you write is these 2 lines. You only write a line defining your type, what type you want to put in, and of course the attribute macro on top. And everything else is being basically generated for you. All of this code is being generated for you. Like this all of it is being generated. Like this, all of these traits, all of these get set functions, like the reason why after writing this, I'm able to call get is because something in the macro is generating all this code for me.
What about the underscore there? Like, is that...
This underscore is again, that's what the prefix is. This palette macro is populating this for me. So the underscore is kind of like hidden, but it's basically, it's taking a struct prefix and sticking it in.
It seems a bit hacky, the underscore part.
Well, underscore is a real thing in Rust, right? Rust, it's inference, right?
Of course, but then like, are we allowed to put something that's not underscore
yes.
there? Okay, so
if you satisfy this interface, you can stick whatever you want in there.
So what's the meaning of underscore?
Underscore is
not in the Rust syntax sense. Like, what does it mean here when we put underscore?
It means that the macros should generate for you this prefix. Like,
so basically, you're saying default.
Yeah, default.
Prefix.
Yeah, exactly. I mean, that's exactly what kind of Rust is too, right?
Underscore is.
Or like it's like inference.
Yeah.
Yeah. So in this context,
it's like
again,
unnamed.
So
well, it depends on the context.
But here's the deeper picture here. When you're designing your palette, you don't know the name of your palette, right? That's defined by the runtime developer. So we've done for you already, like grabbing your palette name and making sure it's unique and put it in for you. So this is we're doing all this stuff for you.
It just seems like it would make more sense to have like a type that would just have one type arguments.
Okay, but I think maybe that's perhaps true. What I would say to you is this. If you believe me that this is how this code works, you would also, and you've already used these low-level functions, right, yourself, right, directly? You can actually write whatever you want. Like the point is, Frame is an opinionated framework. We have designed things in the way that we want. You know that as a runtime developer, you can actually build your own Frame. Make Frame 2.0. Do however you think is best.
Yeah, cool.
Great. Yeah.
So what if we pass any value over there instead of underscore?
Instead of underscore. I mean, if you do it, you're like shooting yourself, not shooting yourself in the foot. You're like, you know,
Is that taken care, or that will be error in this frame?
it will work as long as you satisfy this trait. That underscore must satisfy this trait storage instance. There is some trait called storage instance which has const storage prefix. I mean, I can find it for you. Like, let's do it. Polkadot SDK trait storage instance. So there's literally a trait. I'm not lying to you. I mean, there's a few more. There's a few more things in it, but there's a palette prefix, which is some function which returns a string. There's a storage prefix, which is some const. I mean, that's basically, I'm giving you the thing here. There's a palette prefix hash, which is literally just hashing that value. I mean, there's a prefix hash, which is copying these two things and concatenating them. Like, I'm sure, I'm not lying to you. This is literally the code written down here. So if you satisfy this trait, then you can put whatever thing you want.
So for now, while using this, it has to be underscore and only underscore for now, I believe.
Oh, you're saying to me that you can't replace it?
Yeah, I mean, while using this, we have to leave it like underscore.
I don't think you have to. Are you saying you have to? Are you telling me, or are you asking me?
No, I'm confirming my understanding that we have to keep only underscore as per this implementation.
No, I think that you can. I think that you could make your own struct with your own custom names that satisfy this trait and put it inside of underscore. Okay, but in that case, you're like bypassing the standards. Right? And there's going to be other compatibility issues. But, you know, we are not forcing that, you know, it's just, you know, the macros are generating this stuff for you. But again, when I say this stuff, like, it really is this simple. It's really exactly what I'm telling you here. Okay. So again, this is how this key is getting generated. This is behind the scenes of what's going on. Right? You don't need to know this, but it's just, this is behind the scenes. It's generating this. And I can show you this. We can do a cargo expand of one of the palettes. You'll see all of this code. Okay. So can we move on, or any more questions about keys? Okay. End of the day, just know that keys are the prefix. We're going to go even more into why that's useful later. Another thing to note, let's go back to this thing, that when I get the item, it returns none. I put some item. When I read the item again, it gets some. So in this case, all storage is an option, right? And that's the right way to do things. All storage is either some or none. There's either some value in the storage or there's no value in the storage, right? And so at the storage level API, it will always be an option, right? So none versus some. However, we can hide this with a default value. And so what I'm going to be going over the next slides, I'm going to be showing you, where is it? All of these different configuration parts. So there's a query kind and an on-empty default. Like that. I'm going to show you how to configure these things. So the most simple definition of a storage value is this. Just two fields. But you can actually define a default value and use more fields. Because I'll show you that later. Let's see. Query for storage actually exists. So there are APIs which expose you to whether the value actually exists in the database. So in this case, you have a storage value U32. If we query, does this item exist? Before we do anything, we get false. If we try to get the item, we can get none. Okay, nothing is actually in the database yet. But this is a little bit interesting. Query kind, option query. I'm worried that I skipped over one important part. All right, let's keep going with the slides, but there's one piece I want to go back to if we missed it. I apologize if I feel a little unprepared here. I think the order of my slides are a little bit weird to me. Okay, so we have here, you know, you can basically query, does the item actually exist in the database? Is there actually a value there, right? Query kind. So we have those two other items here, right? So the most simple one only had these two items. Now we can also introduce value query. We want to change it. So instead of by default, we have an option query. We can actually say we want to have a storage with a value query where we return a value when there's none. And by default, it's the default value. So in this context, we have item 2. This is a new value that stores a U32 with a value query. In this case, when I call get, I'm not going to get none. I'm going to get 0, right? And when I do put on 10, and when I call get, I'm going to get 10. So it gets rid of the option type and just gives me a value.
Is there a way to know whether it exists? Okay, because if it's all.
Yeah, okay. And remember, this get, this 0 isn't actually in the database, right? There is no 0 in the database. There's actually nothing in the database, but we are falling back to the default value. You see, with this API, you will.
They exist.
With this API, so if you query 0, you do not have enough information to know whether it exists or not. But there's an API which can tell you. That's correct. Last thing is this, you can control this on empty value. So if you go back to this first thing here, right? So the default query kind is option. If you don't include anything about here, it'll be option type. I showed you now that you can be value type, right? The other one is default on empty. The default option is get default, which is why it's 0. But you can also change this too. So here we have value query instead of option query. And here we have the on empty. So in this case, I can define, using this macro, type value, my default, and I want it to be 42. And I can then define a storage item where it's a value query, and my default will be the default value. So then, when I query the item when nothing's in it, I'll get the value 42. This test pass, right? And then I can put 10, and then afterwards I get 10. So all of this is configurable for you, right? So you saw, in the easiest case, it just looks like this. But then you have some additional type parameters that you can adjust the functionality of these storage things, right? Quite flexible, yes. And remember, 42 is not actually in storage, right? It's not in storage. It's just some logic back here.
So the my default is basically some function that the consumer of the palette would define, because it's like item 3t. T means config, right? Like, because in my default.
Yeah, I mean,
I see.
you could make this configurable, but in this case, it's not configurable by default. The T is coming into the stuff.
The T there. So
it's
the T
it's
item
different.
is the value. What is T in?
Yeah, this is where, if you have that question, you should do the Rust state machine. T is coming in because you are working in the context of a palette, which is generic.
Yeah, okay.
Yeah.
So
in this case, okay, I can actually give you a better answer.
No, because like in my default T config, T is the config.
Yes, T is the config.
In
but
item 3,
in this context, T is coming in because I think that the thing like the palette name and other stuff like that that's used for the key is coming through the T config.
Okay.
In general, when you're working the palette, almost everything uses T. Everything is generic.
I know, but it's just like T config usually. But yeah. Okay.
Oh, why is it T config? Okay, yeah.
No, this I understand. I don't understand why it's not T config in item 3.
In this second one.
Yeah.
It's not T config here because we're not actually using any generic types.
So what is T referring? It's up to the.
It's an unspecified generic parameter. I really think that you should do this Rust state machine.
No,
like this answers that question.
Okay.
Okay? Yeah.
I still don't understand how can we query dynamic values, because in this example, like the key in the database would be the palette name and that specific configuration. So if I want to have, for example, in the storage, like for each user.
Yeah, I'll answer that. I will show you storage map. So storage map adds the account as an additional hash.
Okay.
Okay, I'll show you that. Okay. So I want to mention this is not magic, right? So so going back to this, setting this default 42, you can use the substrate mechanisms for doing this, but you can also just have a default item 1, that's item 1 without any of this optionality stuff, and then do try get unwrap or 42. This is the same thing. This is basically what's happening in the background. So it's kind of like, it's all ergonomics, right? Maybe in your API you want to deal with options, so it just saves you this work. But nothing here is magic. It's just literally in the background generating this code for you. Okay? Okay. Set versus put. So it's interesting, we have two different APIs here. So you now knowing that there's two kinds of query kind, set is actually setting a value based on the query kind. So if you set it as an option, it will set as an option. But put is always putting a raw value. So in the context of item 1, which is using an option query, Here you put sum 42, or you set sum 42, or you put 42. Okay? Now, if this was, do I have an example? If this, I don't have an example here, but like if this was U32 comma value query, you would set 42 and put 42 because this type matches the value query. Again, things you can play around with. Like I look at my example, you can mess with things, okay? But there's no difference between these two calls, right? There's no difference. One thing, this is a common pitfall. Don't actually put the option as the storage value. That doesn't make any sense. Storage values are already options. By adding an option to the storage value, you're adding an extra bit to all of your code, or an extra byte actually, right? So you remember the scale encoding, right? An option adds an extra byte, which tells you whether the option is okay or not. So let's look at this example. Okay. Item 4 and item 5. One, item 4 is an option U32. The other one, item 5, is a option U32 value query, right? So to start with, item 4 and item 5 don't exist, right? If I put none into both, they will both now exist. Even though I'm putting nothing into storage, you are actually storing 0, 0 into database. So in both of these cases, where you have option as your type, you're basically storing extra data you don't need. It's not just you storing 0, 0. You're storing a whole Merkle root thing. Like it's a lot of overhead for that item. So you should never put option here. It should just be U32 with the option wrapper around the storage. But then when you put none, it'll delete the item. One more time? Yes, exactly. A 3-state Boolean. Exactly. I mean, that could actually be maybe a useful case for it. Yeah, perhaps. Okay. One more question here in the front.
There you go. Go back to the previous slide real quick. I just want to make sure here. So without the option wrapper for U32, if we go ahead and try to put none in there, if we call exists for both of them, would they return false in that case?
I believe the second one is a value query. So if you don't put option, you don't have access to that thing. Mm-hmm. But the first one is an option query. If you put none, it will delete the value.
Gotcha. So it would just return false then.
It will return false.
But for a value query, it will return true.
Well, with a value query, you can't put none because it would be a U32, right? So it only accepts a U32.
Gotcha. So
there's a different API. I think is this the next one?
Would just not compile or would just panic? Or?
There's an API for remove. So you could delete. You could just call delete, and it would delete the item.
Gotcha.
That's a different API, right?
Gotcha. Yeah.
Okay. Okay, next. Another thing that you want to do to maybe optimize, this is like micro optimizations, is use the unit type instead of a bool, right? So rather than storing true or false into the database, that's like actually storing some value, you could actually have a storage value of the unit type. And then if you check if it exists, false, if you put the unit type, true. I mean, this is quite a micro optimization, but basically you can save 1 byte. By instead of putting true or false, you just use the fact that you know it's an option. You can do it, and this is a real use case. No, unit is no bytes, right? Yeah, the unit type. If you should do this. You have the scale thing. Do scale encode of unit. It will return empty array. And in this context, what does that mean? Remember those nodes? The value there will be no value there, right? So it actually saves you 1 byte. But again, the truth is, this is a micro optimization. You understanding this is a trigger that you understand kind of the layers of what's going on here. Practically speaking, use true or false if it makes your code better. Like in the blockchain world, you are more concerned with someone being able to audit your code and understand your code easily, right? That is worth way more than this 1 byte, right? But this is a mental exercise. Do you understand what's going on in these layers? Do you understand what's being written to the database? Do you understand scale encoding? All of those things come together to make you understand why this is technically better. Another question. Yeah, let's get this guy a mic. Can you?
I'm just like a bit confused here. So is it? It will be. So what are we doing when we put? Because we are putting.
Perfect.
Right?
Let's go back to this. What we're doing is we're creating a branch node with no value. Like the existence of this branch node means that that's the true or false. Does it exist? Does this node exist? And then where this value is, there'll just be no bytes.
Okay. So the
But
node
this
itself,
node will exist in the Merkle tree.
and this has whatever like byte or like because the node itself has a size because it's saved.
Yeah, so
everywhere.
there will be some size taken.
Yeah.
You're saving 1 byte. You're saving this 1 byte here. But you still are using all this. There's no way around using all this, but like you're saving that 1 byte on the value.
Yeah, so I guess for my context at the very least, would this, like, if you were just to use like a Boolean value for your value, basically for the source
Yep.
value, would the compiler just compile it down to this code basically, or would it?
No, the compiler doesn't understand at this level, right? This is a framework built in Rust. So when you do true or false, it will encode true or false, which is 0 or 1, and then put that in the database. Like it doesn't know your intention here. It's not that smart.
Gotcha.
Yeah.
I guess the more of a comment here, I can imagine, like, since obviously you're just storing true or false in this case, you could probably make something like this into like a storage mechanism for other bytes.
But I think you're saying, can we automatically optimize this, right?
Well, I'm more saying just in a theoretical sense. I'm just throwing stuff at the wall here, but maybe you could use this as some sort of like I won't say Turing machine in regards to like I don't know if this makes any sense, but you know, storing like a binary data for like true and false. Could we basically more or less make this sort of like storage value into some sort of like storage mechanism for other piece of data, if that makes any sense?
It doesn't make sense to me because why wouldn't you just like, store whatever data you want to store?
Well, yeah, it's more of a thought experiment in regards to like this sort of like storage mechanism.
Yeah, I'm sorry, I'm not following.
I'll talk to you about it later.
Yeah.
I think I probably just flesh my idea. A little
Yeah,
bit
I'm
more
not following along, but basically this, like,
Yeah.
we have an arbitrary key value database. We have a method to encode every value using scale into thing. We just put that data in there. If you want to put some data in there, you just put it in there. I wouldn't do it any other way, especially not playing with Merkle trees.
Got it.
Okay.
Thank you.
Okay. So that's interesting. So there's obviously now an option to kill storage. So someone mentioned that. So here I have a storage item 3. This is the one using the value query and the default of 42. Initially when I query it, it's empty, so I get 42. I then put 10 into it. Now I get 10. I then call kill or take. These are two different APIs. And you can see then it removes the value. And then the old value, then when you query it, it gives you 42, right? So kill directly kills the item. Take kills the item and also returns the value. And then you can access it if you need to, right? But you can see that when you call that value after, it's 42 again, because that's the default value. Now, question. What is the advantage of kill versus take? Why wouldn't we just use take every time? The answer? Yeah. The mic is right in front of you.
Because you don't retrieve it back from the database. That's
Perfect. That's exactly correct. That in the case of kill, this is, okay, ready?
And it's true for get also.
We talk about the layers, right? The layers. In the case of kill, all I have to do is write to the overlay, kill this item. And at the end of the block, it will kill it. If I call take, I need to go read the item from the database so I can retrieve it from you and then write kill. Does that make sense? So literally, if you're going to call take and you don't actually use the value, you're forcing yourself to read the database. Whereas kill, I don't care what the value is there, I'm just going to kill it. So there's this is a whole extra read to the low-level database than this is.
It's true also for exists, no?
Exists, you always have to read the database. There's no way around it. The advantage of exists.
There is something of a thing.
Yeah. So the difference between exists and get.
Yeah.
Exists it gets to the leaf node and doesn't deserialize the value.
Exactly, yeah.
Get, we'll have to deserialize the value. Now, deserialization of like a simple value, basically nominal. But if you have like an enum with an enum inside of it, with a struct inside of it, like deserialization can be
I
expensive.
think there's also about the encoding of the key. Like we had this in assignment 0.
Yeah.
There was a question like, what do you think this should be better or something? So I think
Exactly. It's that. These are micro optimizations, but they're real. Again, it's not about you should do this perfect every time. It's that if you understand this, then you will understand better how to program what's going on. At the front, could you take the mic, please?
Is it take equivalent to the get and then kill? Like
It is basically equivalent, except get and then kill is 2 times going to the overlay. Take can go to the overlay once, do both operations. Right? That makes sense?
so it's cheaper, right?
It's like you know, barely cheaper. Yeah. Like I would not like again, I think that kind of optimization, if get and kill is more easy to read as a developer, do that. It's not worth whatever that one small thing is. But take basically is better. Okay, mutate. So you also have the access to mutate an item directly in place. So I can put some value into item 2, and then I can call mutate and use a closure on that value, do some operation, and by the end of this thing, it'll update the value, and I call get, it gets the new value, right? So mutate basically is a closure acting on that value. At the end of the closure, it writes the value. Okay? And this is equivalent to get, do some code, put. They're the same thing. Yeah.
In this mutate one, if some arithmetic error happens,
An error happens. So this mutate cannot return an error.
yes.
This closure cannot. But there is something called try mutate, which can return an error.
Okay.
So mutate is a function which accepts a closure that always succeeds. Try mutate is a function which accepts a closure which can return a result. And in the case where you return OK, the value is written. In the case where you return error, the value is not written. So here, look at this. So divide by 2. If x mod 2 is 0, okay. If x mod 2 is even, okay. If not, error. So 21 is not even, therefore it will not write the value.
Okay. So in case when should we use mutate? Only if we are sure about no errors?
It's not that you're sure. You cannot, like Rust, you cannot write a function. Like, it's not JavaScript. You literally, Rust will not compile if you can't return, if you're trying to return an error, right? It's like, yeah, it makes sense, right, what I'm saying?
I got it.
Yeah, like Rust will not let you write any code except one that only succeeds. Yeah, question over here.
In this slide, what if item 2 doesn't exist? Will mutate still success?
In this context, item 2 is the x, this x will either be an option or be as some value, right? So in the case that item 2 is an option, this will be none. And in this code, you have to handle none or some. Or in the case of the default value, it will be 0, and this will act on 0. So it will always execute, but you will just, that this x value is either that option or it's the default value, depending on how whatever item 2 is, right? That makes sense? Okay. But again, I actually, in general, don't prefer this. The advantage of mutate is you can never forget to write, right? Like this will automatically write for you at the end of the mutate. But generally speaking, I prefer to call get, do the things, and do write at the end. For me, it's just simpler to read. I'm not stuck in this mutate with the additional closure and the additional indentation. It just makes more sense to me. But I'm sure there have been people who forget to write the storage and then have a bug, right? But these are all options for you, right? You are the developer. Here are the options. Okay, so you might have noticed in this test, we use this thing called assert no-op. This is what you guys should be using in your tests. Assert no-op is just like assert error, except it also checks the storage root has not changed. So this is exactly the code in Substrate for assert no-op. It checks something happened and that a specific error was returned, the matching the error, but also checks before you do the operation and after you do the operation, the storage root hasn't changed. So this guarantees that there has no magic writing happening to the database. So whenever you're doing tests in your system and you're verifying errors, you want to ensure that the errors are not actually accidentally leaving behind some data that you might not expect, right? This is going to happen if you're manipulating storage layers, right? If you're doing storage layer magic, right? You might think, oh, this is something that unwraps everything undone, but actually you could be writing to data. So using storage no-op ensures that the storage root hasn't changed. Okay? So anyway, inside of your runtime tests, you basically never use assert error. You almost always use assert no-op, okay? Okay, vectrix. So going back and combining our knowledge about scale and storage, we can do some tricks with vectors, right? So here we have two APIs, decode length and append, which work on a storage value with a vector and allows you to do things without decoding all the items. So in this case, item 7 is a vector of bytes. I can call, if I wanted the length of this vector, I can call item 7 decode length, and it'll return none. That's because nothing's in there. I can put an item, one item in there. I can call the decode length, it will return 1. I can append 2 items to it. I can get it, it has 3 items now, and I get the length. So what's the optimization happening here with decode length? Why is this optimized? Well, so the thing you could do is you could call get, and then you could call dot length on that item, right? But doing this way, I don't need to deserialize the whole item. I only need to deserialize the first bytes of the item because we know vectors have prefix encoding, the length prefix, right? So if I want to know the length of a vector, and it's a really long vector, I only need to look at the first couple bytes to get the length. So this is doing that optimization for me, right? If I called get, it would have to deserialize the whole structure. So here, we are going down to the database. We are fetching that big chunk of data. We are bringing it up. We're just choosing not to deserialize all of it. We're just choosing just to read the beginning bytes. Okay? And same with append. With append, I don't need to go down and get the vector to then add items to it. I can actually queue the append in the storage overlay and then do the actual vector append at the low-level database. So in this case with append, I never had to read the vector. It's just code. It's just you write a bunch of code that handles these situations. You could call get, you could call push on the vector, and then you could, or call append on the vector, and then you could call put. But this is faster because you don't need to retrieve the rest of the vector. And I think I actually even have a slide on how this optimization here gave a 90% increased speed performance to Substrate. 90% performance increase. I have a slide on this, I believe. Okay, so you might have noticed here, we are dealing with a vector of U8. I had to put this palette unbounded to be able to support it. Okay? You have to remember that blockchains are limited in computation time, memory limit, storage size. Actually, in fact, blockchains are very much like embedded machines, like very small microprocessors, right? Like they are very, very limited in resources, right? So in general, every storage item in frame should be bounded in size. You cannot put into storage unbounded items because this would potentially screw up the proof size. So in this case, I'm bypassing, like if I didn't have this line here, the compiler would yell at me, would say that vec U8 is not bounded, right? But I can put this here and I can, again, shoot myself in the foot. Or I can know better than the compiler, right? These are all options for you as a runtime developer. We will discuss more about boundedness in benchmarking, okay? But instead of using a normal vector, you can use a bounded vector. And I think you all built this in your assignment 0 or whatever, right? Like this, you had some experience with bounded vectors. But the idea is that you can define a vector which uses in a zero overhead way the ability to guarantee that this vector will only have 100 items. Like this is done with 0 overhead, right? So you give some get u32, which tells you the maximum limit. And then you can see here on this kind of item, I can't call append, because append only works on a normal vector. I can call try append, and try append will return an error if there's a problem. So in this case, I have a vector with a 100 limit. I can call try append 100 times. It will all work. But then one more try append, it will fail. Right? Okay, so that was all of storage item, storage value. Are we all mostly feeling okay? Like these are all the APIs around one value. Now most of these APIs are basically the same with storage map, so it goes much faster. But we all feel good about kind of the APIs exposed to you. Okay, great. So storage map, that was the next question, right? How do we handle storage items where there's additional data or additional keys? So we follow the same thing. So there's a struct storage map. It still has this prefix, but now we have a hasher, a key, a value, and then the same thing, query kind on empty and stuff, right? This exact same stuff as we had before. And also max values. And then the storage key for a storage map is the hash of the palette name, the hash of the storage name, and then using this hasher, the hash of the encoded key. So we use this hasher on this key, and that becomes the final piece of this puzzle. So that's why now we have multiple accounts. They all have their own key. Here's an example. So here's an example of a simple definition of item 9. Item 9 is a map from U32 to U32, where we're using the Blake 2128 hasher for the key. Okay? So in this case, I can insert a value into key 0 of value 100. And then I can get value 0, I'm going to get sum 100. But if I get key 1, I'll get no value, right? Because nothing is there. Very basic. Insert and get. Storage map key. So with a storage map, you can introduce a key and a value of arbitrary type, right? And then for the storage key, we use the hash of the key, and you can choose the hasher you want. This is kind of a micro-optimization as well, but you can choose the hasher you want. So the ones available to you are identity, that's not hashing it at all, Blake 2128, Blake 2256, 2x, 2x, 2x and cat, 2x and cat. We'll talk about these. They're special. These are very special, okay? So let's look at an example of balances. So this is an example of using a value query and it being very relevant in a map. So if you wanted to make a storage item which stores the balance of users, right? By default, all those values would be options, right? But that's kind of inefficient. When you query a user, you don't want to get none or some value. You just want to get 0 or whatever the value is, right? So in this case, it's a very good use for the value query, right? Where, yeah, normally these would be addresses, but basically I can insert Alice has 100 tokens, right, into the balance. I can then create a function called transfer, right? So transfer is a closure. It will try to mutate from the from account, try to mutate to account, and then do the balance, check add, check sub, and resolve, right? This is kind of a more complex way of writing it, but it totally works, right? And in this case, when I transfer from Bob to Alice 10, not enough balance because Bob has no balance. I can transfer from Alice to Bob 10, that works perfect. Alice to Bob another 100, she doesn't have enough, right? And I can see at the end, Alice has 90, Bob has 10. But the idea is that in here, I would have done a bunch of option checking if I didn't have a value query. Because I have a value query, Bob by default has 0. I'm able to just add, numbers to 0. Otherwise, I have to do this is option match, unwrap, all this kind of crazy stuff. The value query makes a lot of sense in the context of something like a balance, right? Saves you some code. It's right here. This definition of this item 10. Item 10, value query. So when I query Bob and he has no balance, I get 0. I don't get none. That's what I want. Okay. The magic of all this. Why did we decide to take a bunch of hashes and concatenate them together. Because in the context of a Patricia tree, these create prefix trees. So all of the storage items for the balances palette will all have balance, the hash of balance at the beginning of the key. So all of that data will be organized together. So all of the data around the palette is all kind of shuffled into its own piece of the Merkle tree and separate out, right? And this is really good. So do I have another slide on this? No. I believe in the substrate storage, we talked about unbalanced trees, right? And how unbalanced trees are bad. Now, unbalanced trees are bad. Why are they bad? Because if a tree is unbalanced, the amount of complexity it is to access a storage item could be greater than the predicted O of n complexity, right? So for example, if you have 1,000,000 items in a base 16 tree, I believe it takes, on average, and it's balanced, it takes on average 5 queries to get to that storage item, right? Because everything is evenly balanced. If you have all of the keys over somewhere else, it could be 7, 8, 9 queries to get access to some value, right? And that's really bad. That means that you're doing way more operations than you expect. If you allow a user to make your tree unbalanced, that's bad, because then you allow an attacker to attack your chain. But if you, the runtime developer, can actually take advantage of unbalanced trees to make other parts of your code more efficient, that's great. That's what we're doing here. We know on a blockchain that there might be millions, if not billions of accounts in your Merkle tree. Why is it that you have to put everything balanced so that accessing any value requires 10 hops? If instead we put all of the balances in one arm of the tree, then accessing other palettes is much more efficient. Are we making this? That an unbalanced tree controlled by a user is an attack. An unbalanced tree that you control and that you're doing intentionally is an optimization. Right? I have now made, because of these prefix trees and putting these palettes in their own thing, I have made the complexity of the palettes independent of each other. So when I'm talking about complexity, I'm looking in the context of a palette. And this is all due to the prefix trees, right? That balances, they all live here. Total issuance is easy to access. But all the accounts, there's no way we can avoid it. There's millions of accounts. There's nothing we can do. But because we do the prefix tree, we're able to separate them all out into their own little unbalanced tree as an optimization. This is the power of using these prefix roots. This is why this is the best way of doing it. If we were just simply to generate a random hash for the whole value, we would basically be intermingling accounts with other storage items, right? This would be inefficient for the whole blockchain. So someone had a question. I think that this answer. You feel good about it? Yeah. Mike is here. Mike.
I'm happy with the prefixes themselves, like having balances and other palettes, and makes sense. But then we can make it in a way that the balances is a prefix and then having a hash map of a hash map, basically. So accessing the accounts afterwards is a O of 1 instead of log n or whatever, right?
No, because you need a Merkle tree or you're going to lose all the properties of being able to have a root hash, right? So if I see, so you're saying instead of having more tree here, at accounts just have a flat structure.
Exactly.
But then we lose the properties of a Merkle tree. Because this item is not represent, like, does it make sense? Like, this is a Merkle tree. Like, if you want these accounts to be part of your Merkle tree, you need to do recursive hashing. Right? Yeah. Now, that being said, there are other data aggregation mechanisms. So Merkle tree is one form of a data aggregator. I forget, there's a data accumulator. There's a Google word there that you can find. But Merkle tree is one. Now, it's a very good one because it supports light clients and it supports all the things we want in blockchain. You can use other data aggregators, and that will work for consensus, but you lose some of the properties of things like light clients. Did they talk about light clients already? Yes. Yeah, so exactly. So you understand why a Merkle proof is so nice with these trees, because a light client can verify one piece of data exists. You could put a different data accumulator here, which wraps all the accounts into just one item, but then you have no way to prove that that data exists without giving all the accounts. So the Merkle tree is basically taking all of the load and heavy work onto the node so that light clients can live better. And this is a mindset for a future of Web3, right? Okay. So let's look at the keys of these storage items, right? Okay, so in a map, so these are from the map, or I guess this is just all the stuff, right? So item 2 was from example. This was a storage value. Item 10 was is a storage map, right? So if we look at all the hashed keys here, you see the storage value is just the palette name plus the storage name. And the storage map is the palette name, storage name, and then the key. This is the hash of 0, this is the hash of 1. So you can see we're literally generating a Patricia tree, right? And this is another reason why Patricia trees are so valuable here. In the context of how we do this hash, there's so much redundant data. This whole hash is repeated over and over again, and we only need to store it one time in the tree, and we navigate, right? So let's go all the way back to this real quick. Way back. You guys remember all the way back here? In this example, I just have A7 as the duplicate data. But the hashes here are quite big. So we're able to, in this context, going to this P, instead of there just being P, we have whole hashes only stored one time. And then we're able to really efficiently store all this stuff. It would be awful if we had all these bytes stored every single time, right? Imagine all of this redundancy.
Does this happen? So with the account IDs, do we also take like prefixes from the account IDs themselves?
No, so the prefixes will happen naturally from the hashes. So we hash the account IDs, and if it happens that 2 hashes start with 9, then it starts doing its work, right? Yeah. Again, the Patricia tree will always be as optimal as possible in this context, right? Any kind of redundancy, the Patricia tree will handle. View, right? That's a big. This is like the beauty of this mechanism. This is what we're doing here. Okay, and finally, because all storage items form a prefix tree, you can write code which iterates the content starting with any prefix. So here's some code, a storage iterator, allowing you to iterate over the entire Merkle tree, starting with some key you can then go through. So if I want to make an iterator, iterating over all the accounts in my blockchain, I can do so by following this pattern of starting with these 2 keys. This is the palette and account. Give me all the subsequent keys underneath it, right? I can basically say, starting here, now give me all keys. And because of this structure, I'm able to do that. If I had everything again be its own hash, separate, there'd be no way for me to actually iterate over the accounts. I have no idea what data is what. Okay? So this is a very powerful decision mechanism for the keys. Yeah, let's do one more thing real quick, okay? And then I'll answer your question. So here, you can iterate on all the blockchain, on the entire blockchain using prefix empty. If you use prefix empty, you can iterate the whole blockchain data. You can iterate all storage for a palette using prefix hash of palette name. You can iterate over all balances of users using prefix hash of balances plus hash of accounts. And again, this is not an inherent property of Merkle trees. This is not an inherent property of anything. This is because we cleverly chose a pattern for generating the storage keys. Using this kind of clever pattern, we have this property. And this is so much more user efficient. Again, you're not iterating keys on your blockchain. You're iterating keys on your UI. If you want to show someone all of your NFTs, you can do that because we have cleverly generated the keys for your NFTs, and you just navigate down the database structure. Not inherent. You had to design the system for this in mind. This is why you should use frame storage. Okay? But there's a problem. I don't know if you guys caught this. Let's say I iterate over all the users' balances, right? I will get all of the balance values because I'm going to get all the storage values. But the storage keys are hashed. I have no idea whose account is whose, right? Because those keys are hashed. This is bad. For this, we use transparent storage keys. And that's what those special transparent hashers are. So that was these two hashers, 2x64 concat, Blake2128 concat. These are special hashers where we take this hash function, takes the hash, and then appends the preimage. Right? So in the context of an account, or I guess in the context of this word hello, hello in bytes is this. The hash of hello is this. The Blake2128 concat is the hash. Where's the B? The hash here plus the actual bytes of hello. So I'm actually able to have a hash function which still does all the magic properties I want. You know, it distributes the keys, it does the prefix iteration, but I'm also able to recover what the preimage is because I include it in the key. Similar with world, right? Exactly the same thing. The size gets bigger, so this is not fixed size hash, right? And that is true. Yeah, I mean you can only have one or the other, right? No, because I have to append this thing.
But the hash of no, that's not a hash. That's a value. Okay, never mind.
Yeah, this is a value. So this is a value, and so if the word was like onomatopoeia, it would be a bigger value. Yeah. Okay. So a better balance map. So instead of the original balance map I had, just use Blake2. In this case, I have a better balance map, which uses Blake2128 concat. So item 10 uses Blake2, which is a opaque hash. Item 11 uses Blake2128 concat, which is a transparent hash. Now let's compare the APIs between these two. So I can do a loop on each of them and insert values into them, right? That's exactly the same. But for item 10, I cannot call iter because I cannot return the keys. Instead, I can only call iter values. I can still iterate over item 10 and get the values, but I can't get the keys because the keys are opaque. For item 11, I'm actually able to call iter, and iter will give me a combination of the keys and the values. So you can see here, this top line, is it too low? No, this top line is the opaque one, where I only get values. The bottom one is the transparent hasher, the item 11, where I'm getting the key and the value. I'm only able to get the key because I have encoded it in the key itself.
Yeah, Marisha. So my question is on the iterating of keys and values. So one thing is we store the path key. It is the hashed account ID. For example, your storage map is the hasher and the account ID. So the prefix and everything. So that will be the path key, right?
Yep.
So and everything with the alignment and stuff, we can still in the storage 10 we can still get the keys, but they will just be opaque.
They would be opaque, exactly.
But we can get the keys.
We can get the opaque keys, the hash.
But then we can use those to actually access the values, but we won't know whose values this.
Exactly. So I'll tell you this. We did this after Polkadot launched. There was one big storage migration where we had to go through the history of Polkadot, find every single account that ever had a transaction, generate a hash table, and then migrate all the hashes to the opaque hasher. That was a giant migration in the first year of Polkadot's existence.
Okay.
But basically, the problem here was that after we had done the opaque hash, people like Yako, who built Polkadot.js API, he was like, man, I can't make these beautiful UIs because I don't have the information, right? So this allows for the information to propagate in a trustless, centralized way versus having like a hash table.
Okay, so one thing is, why can't we just also have in item 10, like also eat and get the keys, like can be useful in other scenarios? Why only including iter values only in the API? Item 10.
So because iter returning key, like in this context, the raw key is not what you're looking for.
For example, I want like ability to kind of get those opaque
raw keys. If you want the raw key, you can call raw key.
Oh, there's
yeah. I mean that's what that's what I've been showing here. Where is it? Back here. So hashed key 4 0, hashed key 4 1. So this gives you the raw key. But again, The thing is that in this context, key, like, again, key, there's two kinds of key. There's the key that you know, the account key, and there's key that the prefix tree knows, which is this key. So you don't want to confuse the two. You don't want the user thinking, oh, I'm getting the key, and then it's like the wrong thing. So there's a very clear set of APIs for the prefix tree, and then there's a clear set of APIs for like the actual account key.
So that's why you said the Black 2 I want to take concat is like a special one because the struct actually like concatenate the
Exactly.
the
It's
key.
what we call a transparent hasher. It actually preserves the value because it sticks the value in there.
Okay.
Okay. By the way, note that when I iterate over the storage, the items are coming in at random order. Why? Because it's reading in the order of the hash, right? When I'm navigating through the keys, it's whatever the order of the hash is. So I'm obviously not getting things in the order that I expect, right? That's just the nature of this decision. So which hashers to use? So now that we know that transparent hashers are extremely useful, there are really only three choices: identity, which is no hash at all; 2x64 concat, which is not cryptographic but transparent; and Blake 2128, which is cryptographic and transparent. So using the identity is, do I have a slide on this? No. Using the identity is good if you know the value is already hashed by you and you don't need to hash it again. Like it's already hashed by you, then don't do it. 2x64 concat is good in a situation where you're controlling the keys and the user isn't. This is by default the best one. I would say for you all, just use this one. There's no reason to optimize. Just use the most secure hasher. The optimization here is basically nothing. Always use Blake 2128 concat, okay? I think I did this one already. Another question? Okay, so I think I did this spiel already. Again, unbalanced trees, not good if the user controls it. Great if you control it. We actually have an optimization in our blockchain because of it, okay? Which hasher to use? We talked about it a little bit already. Read the storage docs for more APIs. Okay, very quick. Storage double map and storage end map. So the storage map was key to value. Storage double map is key 1, key 2 to value. Storage end map is as many keys as you want to value, right? And that's what this looks like. So here, storage map, double map, prefix, hasher 1, key 1, hasher 2, key 2, value, query kind, on FD, etc. And then the prefix, the key is the hash of palette, hash of storage, hash of key 1, hash of key 2. And then end map is basically keep going all the way down forever, right? Here's some examples of using that. So when you define a end map, you pass in a tuple of hashers and keys. And then you can access it by inserting the key as a tuple, right? Map iteration complexity. So iterating over a map is extremely expensive for computational and storage proof resources, right? Like you have to go to this Merkle tree, you're reading all these different Merkle tree items. And reading from the Merkle tree is many database reads, right? It's many, many database reads. So it requires n tree reads, which is really n log n database reads, right? And each of this takes 32 bytes per hash, 16 hashes per node, times n log n proof size, like a huge amount of data when you're reading. You should never iterate on a map. You can iterate on a map. We have APIs for it, but it's not meant to be done in the runtime. It's meant to be done in other Rust code, in off-chain workers, in front-end libraries, anything that's not the runtime, right? It is not good to iterate over map. I do not want to see iteration in your code. I'll say that one more time. I do not want to see storage iteration or unbounded storage iteration in your code.
If I can say like no one's gonna iterate over my map ever, then I don't need the opaque.
No one's gonna iterate over your map in the runtime. In the front ends, they are. Like when I go to a UI, I want to get a list of accounts.
Okay.
Assuming
just
so the opaque hasher is meant for front ends. Sorry.
The opaque hasher is only meant for iteration, I think, right?
It's helpful for iteration, and the front ends iterate.
Yeah, sure. But I'm saying theoretically, whatever. Let's say no one's gonna ever iterate over my map, then I can use a non-opaque hasher, like the
if you don't need the key. But I mean, it's not only for iteration that's useful. Like if you just want to read a value, whose value does this belong to? You don't know whose value.
Yeah, but when I read the value, I have the key.
Yeah, I mean, I guess, but you could, but also you could
That's
have a
what I'm saying,
database.
like only in the
Sure.
scenario of iteration, then you don't know the key.
But imagine this. Imagine you have a database and you found that one key in your database without you reading it directly, but you just see in the database the key is like fucked up. Then you want to say, okay, I wonder whose account is this? I don't know. So having the opaque key just makes sense in general. It just makes sense. The transparent key. What did I say? Yeah, a transparent key. Another question.
You said for the UI, for the front end we want the front end to be able to iterate, right? A list of accounts.
Yep.
For that, you need to expose a function, get me a list of accounts, which will iterate in the runtime, no?
No, the front end library directly queries the RPC which accesses the database. You do not need to expose any runtime functions to access it. The database is already there, and there's this thing called the metadata. You talked about metadata, right? There's a metadata which explains to the front end all of the keys and where things are, and it does it directly. So you do not need to expose a function. Here are my balances for the front end to read the balances. That's actually done through the metadata.
Okay.
That is actually maybe a good point to go deeper on when I do live coding. So maybe if you want, we can touch on that. Okay. Okay. So, but there is a function called remove all, which removes all the values of some storage map, right? So it iterates over and deletes all of them. Again, this function is iterating over all the storage items. So it is as expensive as anything. This is not an O of 1 operation, it's an O of n operation, right? And you can see here that there's some limits we pass. So you can use this function inside of the runtime, but limited, right? So if I want to delete 100 items at a time, that's okay. You can actually write code like that, but it's only 100 at a time, and they have to keep calling the function over and over, right? It's O of n from the perspective of like blockchain reads and writes, and it's O of n log n in context of database, like the actual level of database, right? Yeah. Counted storage map. So we also have, and this is a little bit useful, not used that much, a storage map where we automatically keep track of how many items are in the map. You need to, okay, answer, yeah, go ahead.
Just a few slides back, what is the use case for a double storage map?
Yeah, sure. I mean, the example is the assets palette. Account ID, asset ID, balance. 2 keys to get to a balance.
Okay, yeah.
And then what's the use case for a triple map, quadruple map? It could be like, you know, country, account, asset ID, balance. It could be world, blah, blah, blah. Like whatever, you keep adding more and more keys, however you want to organize your data.
Yeah, imagine compound keys in classical databases.
Yeah, okay. Remove all counted storage map. Yeah, so we have this counted storage map, which is basically a storage map plus a storage value. So I think I have here behind the scenes. So here's the item 13, which is a counted storage map, which is a basic map, and this this item has the ability for you to query how many items are in this map, right? So normally, if you have a normal storage map, for you to know how many items are in it, you would need to iterate over all the items. But you could, for example, keep track of a storage value, which has that number, and the storage map would then, you don't have to query over all the items, you just query the storage value. So this item 13 is exactly equivalent in code to a normal storage map called item 13 and a storage value with the name counter for item 13. This is what the macro is doing in the background. It's just creating 2 items, one with the normal key storage map, and then one with a different name, counter for item 13, which is a storage value, right? And there's some logic behind the scenes which keeps track of how many items. And again, the advantage here is you may want to know how many items are in your map, but you're not allowed to iterate. This kind of tool will allow you to, with one read, get how many items you have. Okay, architecture considerations. We're almost there. We're almost there, okay? You know that accessing very large items from the database is not efficient. Databases like ParityDB are optimized for items under 32 kilobytes. Decoding is also non-zero overhead. You know that accessing lots of storage items in a map is also very bad, right? So lots of overhead, constantly calling host functions, lots of overhead from the Merkle tree lookup and database reads, lots of additional overhead in storage in a storage proof. So you're screwed both ways, right? You put large items in there, you're screwed. You put a lot of small items, you're screwed. So what do? It depends, sometimes both. That's the truth. I mean, blockchain is all full of compromise, right? So let's talk about some scenarios. Scenario A, we need to manage millions of users and support balance transfers. We absolutely use a map, right? In a balance transfer, you're only changing the balance of two accounts, the sender and the recipient. So in this context, we don't need to read all million accounts every time. We just need to read two accounts and we modify those two, right? It's way more efficient than reading one big storage item with a million accounts in it. Scenario B, we need to get the 1,000 validators for the next era. We should obviously use a bounded vector, one storage item with all the data in it, because we're going to need to read all 1,000 anyway. It doesn't make sense to read 1,000, iterate over a map and read 1,000 items. We might as well just stick it in one place. We're not saving anything, any time by separating it out. We are going to read all 1,000 anyway, put it in one storage item. And it's bounded, right? It's a bounded storage item, 1,000 validators. Scenario C, we need to store some metadata and configuration about each of the validators. Here again, we use a map, right? It doesn't make sense that we have 1,000 validators all in one storage and that we put alongside it all of this metadata. When we read the validators, we don't really care about the metadata necessarily, right? So what we can do is we can have a validator list that's all in one item, and we can have some per validator information which is stored in a map. So here, in something like a staking palette, you'll actually be using bounded vectors and maps and separating the concerns. Because when I'm a validator, I'm updating my preferences. I'll put that into a map, right? When I'm querying all of them, I want it from a vec. So in this context, it's actually kind of redundant, right? Because I have here a vector with 1,000 validators, and I have here a map with 1,000 validators and their data in it, right? There's a little bit of redundancy here. But again, it's not about making sure that your blockchain has no redundant data. It's about making sure your access patterns to that data is optimized, right? So when I'm updating my preferences, I want to make sure that pathway is optimized as possible, right? Having a little bit of redundancy in your data, in your blockchain, is a compromise that you make. Summary. Frame storage is a simple macros which wrap the underlying storage APIs. As you saw, down in the details, it's just SPIO, get, set, put, clear, whatever. And we have some macro magic and APIs which convert these names into hashes and the hashes into concatenations and just sticks the data in the location you expect. The principles of substrate storage, the things you learn with Keyon, apply directly to what you can do in Frame, right? All the behaviors and overhead of Merkle trees and stuff like that, they come in when you use Frame storage because it is just using substrate storage, right? It's all just abstraction levels of how we organize the data. Just because something does not exist in Frame does not mean you can't do it. You all have access to these low-level APIs. You have the ability to write your own macros, write your own storage structures if you want to. And just because something exists in Frame doesn't mean you can use it without thinking. Just because there's a storage iterator doesn't mean you can actually just make an iterator and iterate over all accounts and give them all NFTs in an airdrop. This is not good code. You know that a Merkle tree is very expensive, right? Storage is the most important aspect of designing your blockchain. It is where every single dollar of efficiency is going to be squeezed out. You need to really consciously think about your storage structures when you're building your blockchain, okay? And that's it, okay. Any questions?